Between the class, is it fine? Yeah, in the middle of the class. Okay. Good afternoon and welcome to lecture 9. So today I'm going to talk about, okay, shall we start? Today I'm going to talk about the PLLs, and then at the end of the class, if we get time, then I'm going to solve a few questions about the mixers, oscillators, and PLLs, hopefully. So the lecture today is not that long, but very important. Okay. So any question from the previous lectures? No? Good. So first I apologize because I upload this I think a bit late today because I was very busy with preparing the exam questions, but the good news is that the exam questions is very easy, and then I think all of you will get full mark. So, yeah. So we will talk about the exam questions in the last week, hopefully. All right? But yeah, it was very easy one. Actually, not as easy as the assignment questions, but easy. Yeah, it's not. Yeah, I mean, it's not as easy as the assignment questions, but it may be easier. All right. Okay, shall we start? Okay, before I go to the PLL and the basics of the PLL introduction and the components inside the PLL, I just want to have a quick review on the control systems, a little bit of that because I need this during this lecture. I believe most of you know all this stuff, but I want to give something that maybe you forgot. Yeah. All right. So, just some notes. So a second order system in a control system, we define a second order system in a control system as with the transfer function of Hs equal to 2 zeta omega n s plus omega n squared divided by s squared plus 2 zeta omega n s plus omega n squared. So a second order system in a control system, I think we define as this, and I believe most of you know this. Anybody who hasn't seen this before? I believe everybody saw this in linear control. And then we say that in this system, omega n is the natural frequency. If the system is oscillating, then sometimes we call it as a resonant frequency. And the zeta is the damping factor. In here. If we look at the denominator of this equation, then we call this 2 zeta omega n as the system bandwidths. So this is always our system bandwidth. In the second order, this is system bandwidth. In the first order also, you know. And we can define bandwidths equal to omega n divided by q. This is what we had before, for omega naught divided by q. This is the definition of the bandwidths. And then here we can say that this zeta equals to 1 over 2q. So the relation between the q factor of a system and the damping factor, and also the bandwidths, the relation between the bandwidths and the natural frequency and the zeta is, you can see here. Okay, so zeta is this one, and also is mentioned here that the bandwidth also equal to 2 zeta omega n. Okay. For different values of the zeta, we have different types of response to this system. You know that if we had the zeta much smaller than 1, then we call this as underdamped system, and the system has lots of overshoot and oscillation. Okay, I mean, if we look at the response of this system, then it's like this. And it goes high, and then at the end it gets stable if zeta is much less than. And if zeta is greater than 1, much greater than 1, then we call the system overdamped. And so this is in time, actually. And then the response of the system is like this. Takes a long time to get stable. And then we have an optimum zeta. So we say that if we have a zeta equals 2, what's the optimum zeta? What's the optimum zeta in a second order control system? Sorry? 0.77. Okay, so this is the optimum. And then this one is like this. So the difference between this and this is that this is longer. This takes longer to get stable. But this is the optimum, and it does not have any overshoot. Okay? So we always try to design a control system with the optimum zeta because it gives us the best performance that we need. if we write down different types of a second order system, for example, a low pass filter. So a low pass filter, we can say a low pass filter has a transfer function like A naught omega n squared divided by s squared plus 2 zeta omega n s plus omega n squared. So this is the function for low pass filter. I mean, at the DC, the gain, and A naught is the gain, and the gain equals to A naught. If the filter is active, it has gain. If the filter is passive, then the A naught is 1. Okay? So at, for example, s equal to 0, the gain is A. And then at the end, I mean at s equal to infinity, then it's 0, transfer function. If you look at the absolute value of the Hs, so the absolute value of the Hs is something like this. F or omega or S, any of them. Okay. And then the transfer function for a high pass filter we say that it is again A naught S squared divided by S plus 2 zeta omega n S plus omega n squared. So at s equal to 0, it's 0, and then at s equal to infinity, the gain is A naught. So if you look at the transfer function, the absolute value of the transfer function, then it's like this. And here actually we say that this is omega n. This shape, we can say that for zeta optimum, we have this shape. If the zeta is much less than 1, I mean this case, then we have an overshoot at omega n. So this is actually for zeta much less than 1. Okay. And again here we say that this is omega n. And then for band pass filter, we say that the Hs equals to gain A naught 2 zeta omega n S divided by S squared plus 2 zeta omega n S plus omega n squared. And this is the bandpass filter, and then the shape of a bandpass filter is the absolute value for the transfer function is something like this. And then here is the omega n, the resonant frequency of the bandpass filter. So if I want to talk about the stability of this system, something that we discussed in the previous lecture, again we say that in a S-plane, if the zeta, okay, first I just write down this one, that if we have the denominator of the system, which is s squared 2 zeta omega n s plus omega n squared equal to 0, then the roots for this equation equals to S1 and S2 equals to omega n multiply minus zeta plus minus square root of zeta squared minus 1. So this is the S-plane, and then we say that if zeta equal to 0, then what will happen? Where are the S1 and S2? Yeah, zeta equal to 0, this is minus 1, and then multiply by omega n. All right? And then we say that the system is oscillating. So this is for oscillating, for oscillator. If zeta less than 0, then if I just for zeta less than 0, then we say that the system is damped. Okay, and then they are here. Okay, and then for zeta greater than 0, then the system is underdamped, which is here. So in a control system, if we want to control the system, we are always should look at this region. I mean, the zeta should be greater than 0, and also if the zeta equal to 0.7, then we say that our system has the best performance in controlling. Okay? So in the PLL, okay, any question on this? Yeah. Zeta equal to 1. Why? So if zeta is equal to 1, then it's here. I mean, it's on this axis. Okay. This is sigma. This is omega, and S equals to sigma plus j omega. All right. So when we are designing a PLL, then we need to put a filter, a loop filter, and then based on what I said, then we try to optimize our filter and see that, okay, what are the values that we have to take to have the best performance for that filter, okay? So back to our lecture. The PLL we use for many applications in the RF electronics. The main thing is, the main application for a PLL is the clock recovery. So we generate a signal, you generate a signal in a satellite. So assume that we have a satellite here, and this satellite generates a signal, and this signal is V equals to A cosine omega t plus phi. So the frequency of this signal, the LO for the frequency of this signal is this one, okay? The LO signal of our transmitter in the satellite. The baseband, the data is multiplying by this LO and receiving in our receiver. So now what should I do? To recover the baseband signal, I need to multiply again this signal by exactly the same LO to recover the baseband signal. True? So in the transmitter, your IF signal or your baseband signal is multiplied by 1 LO, and then this RF is coming from your transmitter to the receiver, and then again I need to multiply this by LO to get the IF. This is how a wireless link works, okay? But the problem is this LO is generating in the satellite, and this LO is generating in my circuit. So they are different, okay? And what should I do? I should find the LO in the satellite based on a reference signal that I have. And then I try to lock this reference signal to the carrier frequency that I received from the satellite, and then do the down conversion. This LO is generating based on the oscillators that we learned last week. So last week we learned how to make a signal. But to lock it with a reference signal, then we need a PLL. So the PLL architecture is like this, that we assign a reference signal. So this is our reference signal from our local oscillator. This is the signal from our transmitter. So this is the carrier that I received, okay? And then I apply it to this PLL system. So this is our PLL system. And then I receive this F out, or phi or F, no difference, because phase and frequency are from the same category. And then this F is exactly locked to the F that I received from my transmitter. This VCO is generating a local signal, and then the output of this, I try to do a kind of comparison, and then do a filtering, and then apply it again. So this is a closed loop system, and try to control that. Try to control it in such a way that the output of this system and the input of this system are locked together. Okay? Clear? All right. So this is the main application of a PLL. Also, we can use it in the modulators and demodulators. Some of you have seen this in the lab, some of you will see this in the lab. We can apply a FM signal to a PLL and then just recover the baseband signal. At the end of this lecture, I have one slide and I explain the operation of that. And another important is the frequency synthesis. Frequency synthesis means that I have one reference. I have a single reference, and based on this single reference, I can generate different frequencies by programming my PLL, different frequencies out of one reference signal. I can program my synthesizer, we call it synthesizer. I can program my synthesizer to generate 2 of VREF, or 3 of VREF, or n of VREF. This could be integer or non-integer. Okay? And also for the clock generation and clock re-skewing in the digital signals in the FPGAs or in the microprocessors, we use PLL as well. The same thing that we are doing in analog domain, we can exactly do in the digital domain. The only difference is that this low-pass filter is digital. All the calculations that we are doing in the analog domain, then there is in the Z domain. The same thing, everything the same. So we use a phase comparator, digital phase comparator. We use a low-pass filter, digital low-pass filter, and then we use a clock generator, digital clock generator. Done. Everything that we are doing in analog, we are using in digital as well. You see that, for example, they say that the processor is working with 4 gigahertz clock. So 4 gigahertz clock, we don't have any 4 gigahertz clock. We apply a 100 megahertz clock, we multiply it by 40, and then we make a 4 gigahertz clock with a PLL or a synthesizer. So this is a typical, in this configuration you see that we have 4 elements. One is the phase comparator. I will talk about what's the phase comparator and what does it do. Another is the filter to filter out those components that we don't need out of this phase comparator. Sometimes we need a gain to improve the gain of the loop, and also a signal generator or a VCO. I mean a voltage controlled signal generator. So this VCO actually is the voltage controlled oscillator that we saw in the previous lecture. By changing the voltage, the output frequency is changing. Okay? All right. Yeah, the purpose of the low-pass filter is to remove the unwanted high-frequency component. We see that this phase comparator could be a simple mixer. So mixer has 2 components, the difference and the addition. So we are interested in the difference, and then by using a low-pass filter, we can just filter out the sum signal. And the amplifier for achieving the adequate level of the voltage for this VCO, because if the gain of this loop is not enough, then it does not get locked. So we should make sure that the gain of the loop is enough, and we will see this. And yeah, so for the demodulator, actually it's important that the low-pass filter bandwidth is at least the bandwidth of the baseband signal that we have, because the signal that we receive here is the LO plus IF of the transmitter. So it should work from LO minus IF divided by 2 to LO plus IF divided by 2. So the frequency of this one could change by this amount. Okay? Clear? All right. The first component is the phase detector. What does a phase detector mean? I mean, how this phase detector helps us. Assume that we are generating a signal here. I mean, a random frequency out of this VCO. And I want to change the value of this as close as possible to my VREF. So what should I do? I generate a frequency. I compare the phase of the signal that this frequency, that this oscillator is generating by the reference signal, and based on that, I try to change the input voltage of this VCO in such a way that it moves or it shifts to a point that the VD that we receive here is 0, becomes 0. I mean, at the beginning, the difference between this frequency and the frequency of the input is a number. And based on that, we generate an error function here. So the output of the phase detector is the error function that we received. And then we try to change this error function to 0 in a kind of loop. So this error function, again, apply a voltage to this VCO. The voltage of this VCO changes the output frequency changing, again the error is changing, and then so on. Until the error function is reaching 0. When the error function is reaching 0, it means that the output frequency and the input frequency are the same. Or the output phase and the input phase are the same. No difference. Okay? All right. A simple phase detector could be a mixer. How? Assume that we have the input signal of V1. So the input signal is V1, and assume that the frequency of both of these are the same. I mean V1 and V2. The frequency are the same. Because this one, also I can say that this is a phase, and this is also a phase. For simplicity of analysis, I assume that these two, the frequency are the same and the phase are not the same. I mean the initial phase of the first one and the second one are not the same. So the output of this mixer, we know that if the output of this mixer, V1 mixing with V2 equals to A1, A2 sine omega t plus phi 1 sine omega t plus phi 2. So this is the output of the mixer. And then these two, we can just write down the cosine plus and cosine minus, what we have done in the mixer. True? So there are two components in the output of the mixer. One of them is this VL, which we are interested, and one of them is this VH, which we try to filter out through this low pass filter. So this one is in the high frequency, and this one is in DC. And you can see that the output of the low pass filter is proportional to the phi d or cosine of phi d. And then this voltage is again applying to your VCO. The frequency or the phase of the VCO is changing, and then again this one is going to be less and less, and then it gets locked. There are conditions for that, we will see. So the output voltage is proportional to cosine phi d, and then we can also use digital phase detectors instead of analog phase detector like mixer, because mixer use lots of power, and also it's difficult to integrate mixer, for example, in a digital circuit like a FPGA. So in FPGA you can just use logics and use a phase detector as well, and the power consumption is also lower than the mixer. But this is a very simple idea, simple concept. Another phase detector that we can use is a simple XOR gate. So the XOR gate, if we have, again I draw the block diagram that we had here, that we have a reference signal, the output of the phase detector, the output of the filter or the input of the VCO, and our output of the VCO. So if this phase comparator or phase detector, we replace it with the XOR gate. So this one is the phase comparator. If we replace it with the XOR gate, and one of the inputs is the VR, and the other one is the output voltage of the VCO, So assume that this is your VR and this is your output voltage of the VCO. Their frequency are the same, but the phase are not the same. Okay? I want to see that what will happen here. I mean, what will happen to the VC, the input voltage of this voltage controlled oscillator. So the XOR function, so A, B, out, 1, 1, 0, 0, 1, 0, 1, 0. So this is 0, 1, 1, 0. Okay? And then the output will be this. All right? So this is the output of the phase comparator that we have. And then I apply this to a low-pass filter. This is a sample low-pass filter. A low-pass filter active, actually. So the low-pass filter including the gain. Both of these two. I mean, these two is the low-pass filter with the gain. Because the gain of this is actually the DC gain of this is RF divided by RI. So this is the gain of DC. And by playing with these two, we can change the gain, and also by changing the value of the C, we can change the bandwidth of this filter. We can play with the bandwidth and gain with the three components. Okay? So if we apply this signal into the kind of this filter, then the output will be like this. I mean, like this ramp. How? So from, if we set the point, the starting point here, so this one is going to get integrated, and then the voltage increases. So from here to here, I mean that we are changing here to here. So here to here is from here to here. And then can I change the color? Then from here to here, then the VC is like this. I mean, by applying this pulse-shaped signal to a low-pass filter and then to our VCO, then we can change the voltage of the VCO. And by changing the voltage of the VCO, then the phase of the VCO is changing. This is how it works. And the maximum is at pi. I mean, the maximum of the voltage that we can receive is at pi. And we say that this system can track up to pi phase difference. From the 0 to pi phase difference based on the difference between these two, any voltage that we applied, and then it will change the frequency in such a way that these two get synchronized or in phase. Okay? So this is the first component. It can be a digital phase detector or it can be an analog phase detector like mixer. The next one is the low-pass filter. So different types of low-pass filter. We have passive and we can say passive.
In the previous,
yeah.
For phase detection,
yeah.
we are assuming that the frequency is the same.
Yes.
What if it's not?
So in a VCO system, I mean in a PLL system, you can define a phase margin and a gain margin. I mean the phase of the two signal should be inside the phase. The phase difference between the two signals should be the inside the phase margin, and the gain of this loop should be inside the gain margin. Okay. Frequency and phase have the same meaning. I mean, we can say the omega t equals to phi. True. So then I can say that f is a kind of d phi over dt. All right. So this is what we can say. The VCO itself does not change the phase. I mean, does not be the phase shift of the signal. The VCO, when you change the voltage of the VCO, the frequency of the VCO is changing. I mean, the phase of the output phase is changing, because if we write down the VCO equation is like this, that omega t equals to k VT, something like that. I mean, the output frequency changing by changing the voltage input. So it's like that. In this loop, here is voltage, here is voltage, here is voltage, but here is phase, and here is phase, and here is phase. So it's not always voltage. I mean, we are in this portion is phase. If the frequency is not the same, as far as the phase output of this VCO and the reference signal is within pi, you can get locked. If it's out of that, you cannot. It's simple. In a frequency synthesizers, usually we have multiple VCOs for different frequencies. And then we try to control them initially. I mean, when you turn on a frequency synthesizer, so the output frequency that it generates and the input frequency that we apply could be totally different. But then we try to sweep from the starting frequency and then look at the output phase of this to see that, okay, is it locked or not? I have a simulation file here, and I show you that, okay, we increase the frequency, and then when we are reaching close to the frequency of the carrier or the reference, then they get locked. I mean, when we come inside the phase margin, that the loop can be closed, then the system gets locked, and then a stable system never comes out of stability if something special does not happen.
Is that the track range of the...
Yes, true. We can say the track range and capture range. So you have to be inside the capture range. If you are out of capture range, this system never locked, because the phase difference is totally changing. I mean, the phase of this at the time 1 and time 2 with the time 1 and time 2 of the reference is totally different. So they are not going to get locked. But if they are close to each other and inside the detection range, then yes, they get locked. Okay? So when the system starts up, we have to push our VCO to the point that we can ensure that, okay, it's gonna get locked. I mean, if your carrier frequency is 900 megahertz, definitely if your VCO is running and it is 600 megahertz, it's not get locked. But if your VCO is running at 898, then it can get locked to 900 megahertz. All right. We can have different types of loop filters. Each of them has some advantage, disadvantage. For example, this one, the low pass, the simple RC is very simple. So you can pick a value for R, and then based on the parameters that you need, I mean, based on the circumstances, you can pick a number for C to make a PLL. One of the main disadvantages of all these filters is that they do not bring any gain for you. So usually we need a gain in our loop, as we can see here. So usually we need a gain. I mean, the gain that this VCO provides and the gain that this phase comparator provides, because the gain of the whole system depends on the gain of each components. The gain that these two provides are not enough. So usually we need a gain inside our loop. And then the low-pass filter, we need to cascade it with the amplifier, or we can make it, for example, low-pass filter like this, an active filter. This one, the lag lead filter. So we have two components actually to control our loop. We will see that this one gives you more freedom, and this is in more interest. But I'm going to demonstrate the performance of all these filters to see that what's the characteristic of each of them. One thing that you should consider is the bandwidth of the filter. So bandwidth of the filter is a kind of trade-off between the bandwidth and the response time. So if we increase the bandwidth, then our lock time, if we widen the bandwidth, then our lock time reduces. Fast lock. We have a fast lock if we increase the bandwidth. But if we increase the bandwidth, then the phase noise, the output phase noise of our VCO is higher. Our VCO can lock to a frequency, but can change within the bandwidth of that filter, that loop. If we narrow the bandwidth, definitely the lock time is slower. So the time that we can get locked is slower, but the jitter is also slower. Jitter is also less. Also, when we reduce the bandwidth, the probability that we come out of the lock because of the noise is higher, because we don't have that much space to move. And then if the noise inject to our system, then maybe the VCO is changing and come out of the loop, and then the system get unstable and unlocked. And then again, we have to try to get it locked. So these are the trade-off that we have always in PLS. Depends on your application. You need to design a higher order filters. So higher order filters definitely has a sharper roll-off factor and gives you a better performance, but in expense of the cost and the area, and also the complexity of design. The first system the simplest system is the first order PLL. Okay, what's the meaning of first order PLL? We had so this is our phase detector. So this is our phase detector. And this is our VCO. And then this HS is the low pass filter plus our amplifier. Okay. And then we say that this is first order system, and it's just a gain. It does not have any filter. It just gives you a gain to compensate the gain of the filter, the gain of the loop that you need. Let's see what will happen. If we write down the transfer function of this system and assume that this phase detector, we can just replace it with a gain of KD. This, it's better to write down. This is KD, this HS equals to 1, nothing. And then this VCO is also KO over S. Okay, so this is the transfer function of the VCO. This is the transfer function of my filter, and this is also the gain that the phase detector can give me, any number. If we write down the closed loop transfer function, so we reach to this one. You know how to calculate the closed loop transfer function. Closed loop transfer function equals to H of closed loop equals to H of open loop divided by 1 plus Which we opened when we have a negative feedback. We had this previous lecture. If we have a positive feedback, it's 1 minus. In a control system, we have a negative feedback. Okay? So the closed loop transfer function is equal to this. What's the open loop transfer function of this? The open loop transfer function HOL of S equals to KD KS KO divided by S. Okay, so this is the open loop transfer function and this is the closed loop transfer. You can see that the bandwidth of this system is actually KDKO. So the bandwidth of a first order system like this, I mean a bandwidth of HS 1 S tau plus 1, the bandwidth equals to 1 over tau. True? Clear? So the bandwidth of the system is like this. And then the error, I mean, if we look at this point in relating to the input, the error which is phi e divided by phi in, then we can say that the error is coming from this. The main problem with this has advantage. The main advantage is that this is simple, and then it has a very large phase margin. And because of this very large phase margin, then it can get locked for a wide range of the output phase. But the problem is that this HE of S is kind of dependent on the loop bandwidth, which we don't like. I mean that if we calculate the all right, I have one question for you. If we have a signal like V in equals to A cosine omega t. Okay. If we have this, then what is the value for phi in of S?
AS over S square plus omega square.
Sorry?
AS over S square plus omega square. Laplace transform.
Yeah. So Laplace transformer of phi, not V. Laplace transform of the phase of this. I mean the Laplace transform of T itself. S squared, yes. Beautiful. Thank you very much. Okay. So the phi in is this one. If we have a simple sinus, the simplest that we can assume. So the phi in is this one, and then if we replace the phi in here in this equation, then we see that the HE of S equals to, the phi E of S equals to 1 over S plus KDKO, something like that, or it has omega as well with a gain. All right. And actually this one is the omega in, so the frequency that we apply. So here is omega. If I say that this is omega e, this is omega e. Okay. So this is the error function. And then the change of the error function, I mean the d phi, which is s phi s, I mean d phi over dt. When we d phi over dt in Laplace is s phi s. So s phi s equals to omega in divided by I want to write j omega instead of s. So here we have this one, and then I want to say that d phi over dt Laplace of this, which is s phi s, equals to omega in divided by j omega plus k d k o. And this is the bandwidth of your system.
Phi is phi e or phi e?
Phi e. I mean, this is the error function. I want to see that what will happen to my error function. Because at the end of the day, I'm interested in the steady state of the error function to be 0. Okay? So if this should be 0, then what should I do? I want this to be 0. I mean, this never goes to be 0 because of this term. Unless this term is very high. I mean, we have to make a very high gain for our loop that we can achieve a 0 error. This is the problem with the first order filter. I mean, the only way that we can achieve a steady state error function as 0 is that we apply a very high gain to our loop. Then this expression could be 0. This is the problem with the first order. And because of that, we say that, okay, the first order system, I mean, without any filtering, then this is not desirable for us. Okay? Question on this? No? So I should ask question then. So why we can write VCO like this? Okay, this is a equation for integrator. You are true. But why a VCO is an integrator?
Once you detect that they are replacing the period.
You are right. What I want to say that the VCO is a full integrator actually. It's not an integrator to get saturated because we are generating a phase, and then as we are generating signal, the phase increases and increases and increases. I mean, when we are looking at the output of a VCO as it is generating a signal, we always have the phase is increasing and increasing and increasing. If we are not going to, for example, 360 and then get back to 0, then this phase is always increasing. Okay? So this is integrator. But if we write down the function for the VCO, as I already written, that the omega of t equals to, assume that this is the gain of that one, and then this is the control voltage T. So this is the equation for a VCO. True? I mean a VCO output omega or F, no difference, is dependent on the voltage input. And then if I write down this as, instead of omega of T, I write down d phi over dt equals to KO VC of T. Okay. We can write down frequency equals to d phi over dt, true? Yep. And then if I get a Laplace transform from both of these sides, then we have the S phi of S equals to KO VC. And then the transfer function of this, which is, oh my God. And then the transfer function of this, I mean h of this, which is equal to output divided by input equals to KO divided by S. Okay? So this is how we can model a VCO. Clear? All right. Then we are going to, this is what I just mentioned here. And then we can say that the VCO could be, has a gain of KO, and then the equation is KO over S. So if we go to the first order filter, I mean like this one, a simple RC. So a simple RC V in, V out, CR. Then the tau equals to RC, and then the HS, which is the V out divided by V in, equals to 1 over 1 plus S tau. Okay? So if you have a simple RC or a low-pass, simple low-pass filter, then the open loop transfer function, so I just write down here, so this is your, for example, phase detector. If I say that this is your phase detector, this is your low-pass filter. So your phase detector is KD, your low-pass filter is 1 over 1 plus S tau, or tau 1. If this is, for example, R1, tau 1, tau 1. And here also we have a VCO, and it's like this. So the open loop is coming from here, from this one. Simple, this one. And then the closed loop transfer function we can calculate as this. Okay, so this is the closed loop transfer function of a simple RC circuit inside the PLL. All right, so the transfer function of the loop is like this, and if we go back to what we mentioned at the beginning, that in a second order control system we have 2 zeta omega n s plus omega n squared. I mean, if we compare this with this denominator, the closed loop function, then we can simply found that the omega n is this one, and the zeta is this value. What's the gain of this system? So the second order system actually, so this is a low pass filter, true? Because here is low pass filter I just mentioned. The equation for a low pass filter is like this. So this is a low pass filter. And the gain is A naught. All right. So this KD KO equals to omega n squared gain. And then we can say that gain or A naught equals to 1 over tau 1 or 1 over RC. Okay? Am I right or not? No? Yeah. Tau. Excuse me. RC. Okay. All right. To have a best performance for this system, then we have to apply this condition to achieve this shape. I mean, if we apply, for example, a zeta equal to 0.2, then our stability is like this. And if our, for example, phase margin is like this, then maybe when we are trying to get locked, then at this point, then we go out of the lock region. And again, everything is from the beginning and it doesn't work. I mean, we cannot never get locked. Okay? Or if we use this one, then instead of getting locked in, I don't know, in 100 microseconds, then maybe it takes 10 milliseconds to get locked. So these are the problems with the different values of the zeta. And then we try to get the optimum zeta. I mean, define the optimum filter to get the optimum zeta. So then we need to put zeta equal to 1 over square root of 2. And then based on this, we can see that tau 1 equals to 2 KD KO, which is equal to RC. So we know what's the value for KD. We know what's the value for the KD of our phase detector. We know what's the value for KO of our VCO. And then we have to design this. We pick a number for R, and then we define the number for this. Okay? This is an example for what I just said. So we have a PLL like this. This is our signal generator. So our signal generator generates a reference. We use the XOR as the phase detector. And then we use a low-pass filter, RC. So this is our low-pass filter. And then this is our VCO. The gain of this is KO divided by S. I mean the transfer function of this is KO divided by S. The transfer function of this is KD. And then based on what we had, so the frequency is given, the KO is given, and KO is just consider that KO here is hertz per volt, and you have to change it to radian per second per volt. Okay, because then I want to multiply this by volt per radian and then get a number based on 1/2. Okay? Just consider that if you get a value on hertz, you have to change it to radian. So this is the gain of the VCO, this is the gain of the phase detector, and then this KD value is this one, 1/2. We pick a number for R1, 3.6 kilo ohm, any number you can pick. But sometimes we say that, okay, also calculate the R and C based on the gain. I mean, I give you the gain as well, and we know that the gain is RC for this filter. So then you have two equations, two unknowns. And putting the optimum value for the zeta, then we find that the RC should be 18 microsecond, and then C is 5 nanofarad. Okay. Is it clear? Yes? Almost.
So we have two unknown, and then we kind of fix the first unknown to find the number.
Yes. You have two unknown. You pick a number for the first one and then find the C. In this system, it's like this. All right. So this is the simulation that I just told you. This is actually your question, Nishna. So the frequency, this solid line. So this solid line is the input frequency. And this dashed line here is the output frequency. You can see that the input frequency, when it is very low, for this case, you saw that the frequency that we had is 10 kilohertz. I mean, if it is 10 kilohertz, then it gets locked. I mean, if we are, I don't know, this is in, I think this should be 10. Or maybe this one was 1 kilohertz. I mean, when we are approaching 1 kilohertz, then we should get locked. I mean, we should expect that we are getting locked. So assume that we are generating a signal 500 hertz. So 500 hertz, and then this one is far away. And you see that it cannot get locked. I mean, the signal, the output frequency is changing. But when we are approaching this, for example, around here, then you see that we get locked. And then these two get tracked and then go to close to each other. And this is the voltage, input voltage of the VCO. Again, the error function is changing a lot. I mean, from, for example, you see that from 2 volt it can go to 4 volt and then come back and then go again. Because the phase of these two signals are not close to each other. When the phase of the two signals are not close, then definitely it's not get locked. But when we get locked, then the phase of these two signals are close, and then just by changing this voltage like this, then we try to keep the output frequency with the input frequency. If the input frequency, I mean, when we reach here, then it is like this. I mean, we don't change it. I mean, when we reach somewhere that we get locked, then we don't change it. Then you see this like a line. Does not change like this. Because we are changing again the input frequency. The voltage is changing. Again, we get locked. So we are going to the error is increasing, and then again, while changing the voltage, we try to decreasing the error and get locked to the new frequency, because we are increasing the input frequency. Okay. And as you mentioned, we have this capture, and I mean the capture range and the lock range. Okay. All right. So I think this side of the class few people are sleeping, so we can give a break. All right. So we can start 4:30. Yes. Could you bring your stuff? Yes.
Sorry, I'm facing a lot of trouble on this
Yep.
question.
Yep.
So the high frequency model that I know to solve, it's like we have the C mu,
Yep.
like just considering that, and then we have the rest of the circuit.
Yep.
What I know how to do it is by Miller theorem, dividing it into CM1 and which is parallel to C pi.
But we didn't cover Miller.
Yes, but then I don't know how to solve it without Miller.
KVL, KCL. KVL, KCL.
But then collector effect is gonna be there in the ZN. No?
Definitely.
Oh, definitely.
It should be. Because you get a feedback from collector to the base.
Okay.
So it should be.
The ZL would be in the.
We don't consider R mu.
E will not.
RO.
R mu. There is an R mu parallel.
No.
Okay.
We didn't have that in.
Okay.
And what about RO? Should we not consider RO?
No need. I mean RO. I mean I didn't mention. I said that okay. Just take care of these two. So you can just write down a KCL here,
Okay.
a KCL here,
Okay.
and a KVL here.
Okay.
And simply find
Like
the
KCL here and
V divided by I.
Yeah. Got it. Now I
No need of Miller. Because Miller, okay, Miller is not working in this structure. What you see, if here is ground, yes, Miller is correct. But when we have a degenerative element,
Okay.
that Miller is not.
we have to apply KCL here and as well as KVL in this loop, right?
I thought that we'll convert this to the base side and then we'll apply Miller.
You can do that, but again, if you want to move this to the base, I mean, then the L that you see here is LE beta plus 1, but this beta is the beta
Beta DC divided
S,
Okay.
which is the GMR pi divided by 1 plus GM plus R pi S C mu plus C pi. So it's different. I mean that then again we have the effect of this. Okay.
Yeah. Yeah. I wasn't just sure about the collector part, how it will reflect.
Yes,
Now I
definitely.
understand.
Because actually the intention of this question is that when we have this CMU, then the input impedance of this structure is dependent on what we put in the collector.
Okay.
Because in the low frequency small signal model of the input impedance does not affect any much from here.
Yeah.
Okay.
Thank you so much.
Yeah. No.
But why should we not consider RO?
Because I didn't say you can consider. I didn't say that. for more, if you want, you can, but it's difficult. It's more
So
difficult.
we can't solve about
It is
the
anyway
KCL.
very big.
You can.
I couldn't.
We can't, but yeah, we can, but it's very.
Yes, this
very
is as
straight.
big as this. Yes,
It's like this.
but then you can assume that few of them is negligible comparing to the others, or one of them is negligible to the other.
So which one we can ignore? We can't ignore.
For example,
So we should say RE greater than R pi.
if you have a component, if you have, for example, three components, okay?
Yes.
One of them is A naught, one of them is A naught S, as one of them is A naught, for example, B naught S and C naught S squared. Then in high frequency, which of them you can ignore?
A not and A not.
For example, you can ignore this because this is much smaller than these two. Or if you have A naught and then you have B naught divided by S or C naught divided by S squared, you can get rid of this. Okay?
But the result is just way too big.
Yeah, it's
It's
Yes.
just
So
too
this-
big.
so there's a lesson.
Okay, I agree that I can ignore this compared to the rest.
Are
but
you
it's-
sure that this is correct?
I just followed what you said yesterday.
Can I have it? Okay, can you?
So it should be divided by this whole factor again. I just didn't write it.
Yeah. Our answer is just like this one.
I think it's not as big as this that you found. It's this big.
Okay, it is this big
think-
because
Because
no,
you
because
are like ignoring
I-
after ignoring so
no,
many
no, no,
things,
no.
right?
Is it this big? This is big.
No.
Smaller?
Yeah. For example,
Okay.
this big.
Mine result is this one.
No. This is very small. And this
This is very
big.
big. That's very small.
So I did it.
No, mine is
you
small,
do
bigger.
DC analysis. I did AC analysis.
Yes, you did AC analysis, but very CMU.
You didn't consider the effect on C mu and C pi.
I didn't consider it because I go from this, then C mu is ignored.
Why? How you can? I mean, when you want to calculate the current in this line, so the current in this line is this current and this current. So you cannot
This is big.
ignore this.
This is big because I have
So I need to
taken it
consider
as
this
R
one.
pi.
Yes.
Then I need to consider C pi
Broken it
also.
down.
Always, both of them, yeah.
Put everything.
But it's not as big as this.
So I can do
This
this
is,
my
it
way.
is this
I
big.
can do this my way, right? After doing this, I can do this my way.
Which one?
This one, first one,
I
the
know.
Z in, I
This
can
is
do
fine. Whatever I
in my
did is
way.
all perfect. It should be.
So
I
this is my
understand
high
it
frequency
can't be
model.
this
I
big,
need to
but
add
it is
the
something
C pi here and C mu here.
Yes,
When we are
and then
taking
you
assumptions,
need to
there
write
no
down, for
assumptions are
example,
taken.
a KCL here, a KCL here, and a KVL here, and then find the
But we
The
know
V
that beta
divided
DC
by
is equal
I.
to beta AC. Beta DC greater than beta AC. We know that, right?
yes, we know, and then beta DC equals to
Beta DC greater than beta AC.
yeah, I think you have is
So
this
this
is
is my beta AC.
yeah,
This is my beta AC.
this is true, but you didn't consider the effect of this in the Z in.
Then if I consider that, then my answer
True,
will be okay.
could be the yeah.
What I'm saying is, I understand it should be small, but mine became so big because I did all the, I took,
Like we open
Like
all
I
the
just-
brackets and
didn't write as parallel and
Why
stuff.
didn't you do that?
Because at the end
Because
I
it's
anyway had
easier.
to calculate.
yeah,
so I
because
just,
they're like
Yeah, true, but you can, for example, write down instead of this Z pi. Okay, put a Z pi, and then calculate the value for Z pi. What's the value for it? It has a number. It's R pi in parallel C pi. At the end of the day, put it there. Or, for example,
but
these
I
three
just want
are
to confirm
ZO.
whether it's correct or not. I found KCL here. This currents
Yes, true.
saying IE is equals to
Yes.
the current here
Yeah,
and GM
yeah,
yeah,
VBE.
true.
Okay. And then
So
Then
one
another-
KCL here and one
one
KCL.
KCL is here.
Yeah, and one KVL maybe here. This is one way
Or,
you can solve.
or
Any
instead-
KVL,
instead can't I
KCL
just
independent.
Put KCL here again, like this is the total current.
Assume that this is
IB.
circuit 1. In circuit 1, we have one voltage here, okay, that I don't know, and one voltage here that I don't know. So this is VO, this is V1, and
This is V in.
for example, this is one voltage, this is one voltage, and this is one current. Assume that this is one current, okay? I have 3 equations. I need 3 equations to
You have
find
to solve 3 variables.
3 variables.
So,
Done.
so KVL
So
will
3,
apply like we'll
it could be
consider them as
KVL or
parallel.
KCL, but they should be independent.
This is exactly what I did, and then these two done, and then here I just put IB is equals, if I just make it 1, then it's this current I1 and this I2.
Yes, true. You are right. So you have the
3
IB,
equations.
yes, 3
IB
equations.
is equals to
Beautiful, I1 plus I2. And then also this I1 is this voltage minus V in
that's
divided by this one.
Yeah, that's all. V in minus V1 by Z.
No, divided by this one.
Yeah, yeah.
VO.
So yeah, this one V in minus VO by.
But I didn't do V O minus V in.
By Z in. This is not Z in.
Z in
No, Z in is just this
Z
two
pi.
parallel.
this one,
Yes.
yeah.
Yeah, Z
This
pi.
one, this one.
Done.
So that's right, right? Approach is right. So we'll just like cut short it and like ignore.
And then
the
you
limits.
can simplify this.
Yeah, just simplify
Just look at this. Yes, just look at this engineeringly and simplify.
Yeah,
All
so
right,
then
guys, this is
in the end
430.
we can calculate individual values and just put it to the formula and get our result, right?
Yes.
It's only this one is set the input impedance now.
All right. After the class, okay?
Tomorrow.
Tomorrow I'm in the help desk 5 to 6.
Where? When?
5 to
5
6.
p.m. to 6.
Okay?
In which one? In
110. 110.
110. Your
No, 110. 110. Where is the help desk?
help desk.
Yeah. That's شنو نه ولی فرستندش تا اونجا که نمیگه شروع شد نه تموم شد چیزا برکشون مادم این بخورم نه نداری نه برای که ملت بترسن مرسی دست شما در نکن مرسی All right, shall we continue? Okay, what we just see here was the first order low pass filter. I mean, out of those filters that I showed in the loop filters, this is the first order low pass filter, and then we saw that how we can design the value for the R and C for the best performance of this filter. So the next one actually is the lag lead. Okay, the lag lead filter, which has 2 capacitors, so it gives us more degree of freedom in designing our filter. Okay? Yes. So the second filter that I'm going to explain here and see the performance of that is the lag lead. So instead of 1 R and C, we have 1 R and 2 C. So this one, the RC is again the low pass filter, and this C2 also gives us a kind of filtering to remove more ripples. Okay, to analyze this, we look at the transfer function here, which is ZS. So you see that the transfer function here is different. Transfer function of the previous one was V out over V in. The transfer function here is the V out over I in. Okay, it means that we assume that our phase detector output is current, not voltage. Okay, it's not different. So if the output of our previous stage, which is the phase detector, is current, then we can use this one. Okay? And then the ZS is the parallel of this path and this path, which is this one. So if you expand that, you will see that the value, the expression is this one. And then if we assume that the C1 is much higher than C2, then we can say that this is C1. Okay? I mean, this part is C1. So this is the assumption that we made to make the analysis a little bit easier. And actually I want, because this is the third order, and then I want to change this third order to a second order filter, and then the same analysis that we have done before. So I assume that the C1 plus C2, then we get this C1. C1 plus C2 is equal to C1. All right? And our assumption is valid if we say that, okay, C1 is 10 times of C2. All right? So the open loop function, the open loop transfer function, again, is the phase detector the low pass filter, and then the VCO, again come back, and then here is the V in, and this is the actually phi in, and this is phi out. This is minus, this is plus. Okay. So the transfer function of the phase detector, we assume that KD is KD. The transfer function of the VCO is KO divided by S. And the transfer function of the low pass filter is this one. Sorry, this one. And then the transfer function of the open loop is just these three times together. All right? So if we look at this one, then we see that it has two poles at S equal to 0 or omega equal to 0. One pole at this one, and 1 0 at this one. Actually, this is minus because it should be stable. I mean, the poles should be in minus in the left hand side. Okay, this is 1 plus SRC. No, sorry. So 1 plus J omega 2 R C2 equals to 0. Then omega 2 is or equals to J over RC2. All right. So we have one pole at this, 1, 0 at this, and 2 pole at 0. Clear? And then, all right, so if we write down the transfer function of this, the closed loop transfer function, so H of closed loop S equals to H of open loop divided by H of open loop plus 1, which equals to, I assume that KD KO equals to K, so KD KO, I call it K. Okay, so this one then equals to K over C1 multiply by 1 plus SR C1 S2 S R C2 plus 1 divided by 1 plus K C1, again the same value, 1 plus S R C1 divided by S2 S R C2 plus 1. So if you write down this equation, you see that this is a third order system. I mean, in the denominator we have S3, all right? But, okay, if I assume that RC1 equals to tau 1 and RC2 equals to tau 2, okay? And I expand this, I see that this is equals to K divided by C1 multiplied by, in the top I have 1 plus S tau 1, and in the denominator I have S3 tau 2 plus K divided by C1, sorry, S3 tau 2 plus 1 plus K divided by C1, 1 plus S tau 1. Am I right or not? Excuse me, this is S2. Okay? It's like this. Okay? So when C2 is much smaller than C1, okay, then we can say that this one equals to 0. I mean comparing to the others, because this one is KC1, and then this one is KC1, and tau 1 is RC1, so this is equal to actually K over C1 multiplied by 1 plus S tau 1 S2 plus KRS plus K over C1. I can say this is 0 because this value is very high. And then I can say that I can approximate this with a second order like this. And this omega 1 actually is 1 over tau 1. All right? So this is exactly what we calculate here. I think so, hopefully. Yes, true. So omega 1, yeah. And K also equal to this. So again, we have a third order system, but for simplicity, we assume that C1 is 10 times of C2, and then we change it to a second order system. The same analysis we can apply here, exactly the same analysis that we had before. Again, we can say that this one equals to S2 plus 2 zeta omega n S plus omega n squared. And then from here, omega n is calculating like this. And then zeta is calculating based on this. Okay. This is omega c crossover frequency. You know the crossover frequency. Crossover frequency if we look at the gain of a low pass filter, it's like this. Okay? Based on the zeta. And then here is the gain of 1, so it's increasing, and then again come back, and again here is gain of 1. I mean at this point. This is omega c. And we call this the point of the phase margin in a control system. So if you look at, this is your H of S, and if this is your phi of S, I mean the phi of your system, then the phi is like this. So phi is 0 and then come here. So here is minus 180, and then here is 0. We call this that the phase margin actually. So from here to the point that we are reaching to minus 180 degrees, this is our phase margin. Based on this omega c and the point that our phase is minus 180 degrees. So this is the omega c or crossover frequency. So we define the zeta is omega c divided by 2 omega n, and then the omega 1, which was here, we defined it, omega 1 over RC1 is again based on the zeta and omega c, we can see this, and then the omega 2 based on the approximation, for example, we assume that C2 equals to 1 over 10 C1, then we can say that omega 2 is 10 times of omega 1. stuff here. All right. So to design a filter like this, again, we put the optimum value for the zeta. So we know that what's the value for omega c. We know KO, we know KD. We can get a number for R and put it here. We know the value for the, and then based on this, we can calculate the C1. And when we calculate the C1, then we say that, okay, C2 is also 10 times or 5 times of that, or 20 times of that, and then this filter is done. Okay? Any question on this? Clear? Good. All right. The last one that I want to show you here is a active filter. So if the gain of the loop is not enough, I mean these two numbers, KO, KD, if these two numbers are not enough, then we use another gain based on the filter, the active filter that we use. Okay? So again, we write down the transfer function of our filter. The transfer function of our filter is coming from here. I mean, these two divided by R1. These two in series divided by R1, and the value is this one. And tau 1 and tau 2 are calculated based on these two formulas. This is your active filter. And so it does give you a filtering and gain at the same time. And then this is your loop. Again, this is your VCO, and this is the phase gain detector and the low pass filter and amplifier, all of them together. This one. Then the closed loop. So if you replace this, then the closed loop is coming from this formula. What kind of filter is this? I mean, based on those that I explained at the beginning, what kind of? Sorry? High pass. Oh, band pass. This is band pass filter. Okay. So this is a band pass filter. And then again, based on this, we can calculate the omega n and zeta. We know the KD. We know the KO, and then we can find the optimum values for this tau. And also the gain that we need. So what's the gain of this system? So if we write down this is, I mean in the denominator it is KD, KO, tau S plus something. Okay. And then the gain should be 2 zeta omega n squared S gain. And omega n squared is this one. So A naught 2 zeta is tau. Okay. A naught multiplied by 2 zeta equals to tau. And zeta is also 1 over the square root of 2, the zeta optimum. Then the gain is tau divided by the square root of 2. Sorry? The gain. The gain is coming from here. Here. So anything that you have in the denominator is the gain. So it is A naught 2 zeta omega S. So then it's different. Okay, so this is the gain. And then you have to equalize that with the value that you got here. I mean, so this is omega n. Okay, so you have to equalize this with this value. You know the omega n, we know that zeta is 1 over the square root of 2, we can find this gain, A naught.
That whole expression is equal to kb times k times.
Yes, A naught 2 zeta optimum, which is the square root of 2 omega n equals to kd ko tau. I'll tell you what's this tau. Yes, this is what it is. Okay, and then this tau, I just write down this as a tau z s, and here it was this one. So this is tau 2 divided by tau 1. So tau equals to tau 2 divided by tau 1. It's like this. All right. So always we go into this equation and then try to find the value for the optimum zeta, and then based on that find the parameters of our filter, if it is passive or active, no difference. The applications of the PLL, if I want to count the applications of the PLL, 2 applications. One is the demodulator, what you've seen in the lab or will see in the lab. I mean that, and the demodulator we can apply it for the FM signal or AM signal, no different. So for the FM demodulated, actually we apply the FM modulated signal as a reference and then try to lock our VCO with the reference signal. Then the input of the voltage controlled oscillator is our signal, is our output signal. I mean, this FM is like this, for example. So the frequency here is different from the frequency here, okay? And then when we apply this to the phase detector and then compare it with the phase of the oscillator, then the signal that you see in the demodulator is like this, that, okay, it shows 1 voltage and then another voltage, so 1 voltage and then another voltage and then again the same voltage. For the frequency 1, it shows 1 voltage here. I mean, the error function is something. For the frequency 2, the error function is something else. And then the signal that you receive here is your baseband signal. But this is the condition that we should consider, that our VCO is linear. I mean, the transfer function of our VCO is like this, is linear. It's not like this, for example. If it's like this, then it's different. If we assume that our VCO is a linear one, linear VCO, F V, then we can use it as a modulator. Or if it is nonlinear, if it's working in its linear region, I mean in the linear region of our VCO, we can use it as a demodulator. Also, we can use a PLL as a reference. What I told you, that okay, I received an AM signal, RF AM signal, amplitude modulated. Use this amplitude modulated as the reference signal to my phase comparator, and then generate a locked version of this LO. I mean, this LO is exactly the same LO as this signal AM modulated is generated in the transmitter. So I use an oscillator, and then based on the carrier of the signal that I received, I try to lock these two and then down convert my signal. And this is actually the low pass filter too, because the signal that we received is the LO plus RF and LO minus RF, and then we are interested only in this one.
And theoretically, L and RF would be opposed to each other as much as possible, right?
Yes. Yep. Okay. And this is actually another application, the synthesizers. I mean, a system which is containing a PLL and also a frequency divider. So this is your frequency divider. So a PLL, and then in the feedback path, we put a frequency divider. Then the signal that I can generate here, if I assume that the signal that I have here is F naught, then the F out could be N F naught. I mean the phase of the signal that I received here, or the frequency of the signal that I have from the VCO. I divided that frequency by N and compare it with the reference. So when the F out divided by N is locked to the F naught, it means that the F out is N times of the F naught. Okay? We use this in analog and in digital, both. But this frequency divider could be simply a digital one, a D flip-flop with feedback, or a T flip-flop. For example, a T flip-flop. So T clock. So this is your clock, and then connect the T to the 1, and then the output. So this is divided by 2. So if this is the clock, this is, I mean, the frequency with the F, this is the F divided by 2. For this one as well, no difference. And then this is another circuit for divided by 3. And we can find another with divided by 5. And then based on those, we can generate anything that we want. Cascading of these, any of these, we can find any value that we want. Okay? The advantage of this is that with a single reference frequency, we can generate any frequency that we want. a multiplication of this. We call this integer synthesizer. Also, we have a fractional synthesizer. I mean, this value could be not only integer. It could be, for example, I don't know, 5.26. Okay. So it has another dividers. So another dividers, 2 dividers here, and then the division between these two. And this could go, for example, up to a number, and this could go up to the number. So you can then exactly generate any value that you want. The fractional synthesizers. And fractional synthesizers available up to, I don't know, tens of gigahertz. Okay. I think this is the end of this lecture. I tried to make it as simple as possible because PLL could be very difficult. The synthesis, analysis of the PLL. I mean, if you want to step into the stability, the root Lucas, then it could be very tough. It goes out of the concept of electronic. It goes mainly to the control then. But the concept of that and how we use it and where we use it and why we use it is what I try to cover. All right. Any question on this? Okay. If no question, then I'm going to solve questions for the mixer and oscillators.
How is this graph plotted?
Which one?
The one
Oh, sorry. I'll open it again. This graph. This graph. Okay. I think so. This actually the loop transfer function. This is the actually this is in log. All right. What we have here. Okay, what we have here is this is the omega c. It seems that this is the omega n, and then 1 over tau. I mean the slope of the slope of this is changing. The slope of your transfer function in the logarithmic format here is -2 and here is -1. What does it say is this? But I have to write down the logarithmic format of this based on the log of omega. I mean, we have to write down this. This is from the book. And then what it wants to say, it wants to say that at these 2 points, it seems that we have two kind of, actually at this point we have a change of slope. And here is this. I have to look at the book. I don't know the description of this, because this is in logarithmic format and this is also in logarithmic format. I need to check with the book to see that what's the representation of this in this one. I think so. I didn't consider this before.
I understand the slope part. That is because of s squared and s. 2 will come down, and there will be two terms like 2 log omega plus log omega something. When we put s is equals to j omega in that, the transfer function.
Yeah.
And then
Yeah, you are right. So when we put the log of that one, I mean when we calculate the log of hs, then this is tau z log of that one, log of this tau z is plus 1 minus log of the denominator, and then the log of denominator is s2. But then how we can separate these elements, I mean, in the log. I will check with the book, I'll tell you. Okay, thank you very much for this question. I think it's a good one. I don't know. It could have some assumptions and then write down those. Okay? All right. Okay, a mixer. The question mentioned that we have a single balanced mixer, bipolar, and then assume that the amplitude is 0.5 volt. Okay, the amplitude of the LO is 0.5 volt. We will see that what's the meaning of the amplitude of 0.5 volt. And then it says that calculate the conversion gain of the mixer and then the output voltage and the rest. And actually if the RF signal is as 1 gigahertz and then the IF signal is as 50 megahertz, what's the LO? So the last part is that LO equals to RF plus minus IF. Okay. 1 gigahertz plus minus 50 megahertz, which is 950. It could be 950 or it could be 1050. But the other part. All right. If I write down Assume that we apply a VRF here at the base of the transconductor, and then we have two switches with the LO, and the signal of the LO is this value. Okay, see that what will happen. If I just want to write down the current that we have here, so the current that we have here, I can say that the current equals to IE, which relates to the biasing current, I mean the DC current, plus IRF cosine of omega RFT. Okay. Assume that we have a sinus, singleton sinus of VRF here, and this is what we have. Yes. So the VRF that we have here, the I that we have here is like this. All right. So this component actually is the DC component, and this component is the AC component. Okay. And then the current which is going into this line and into this line is half of this one. Okay. So the current of here is half of this one. I mean, I can say this one is IE plus IRF cosine omega t divided by 2. Okay. And then what we know is that IRF equals to GM VRF. Okay. So we have a transconductor, it changes the voltage into the current with the factor of GM of the transistor. And also we know that the I out, which is this one, is also equal to GM VLO. Okay, so this is the big GM of this transistor, if we call that I out. All right. And the GM equals to 1 over 1 divided by GM plus this one plus this Z. I call it ZE. Okay. All right. And I can say that this is actually this GM, sorry. This is GM2, this is GM1. GM2 equals to IC or I out, which is IE plus IRF cosine omega RFT divided by VT. Is it clear?
For the transistor,
Sorry?
how is the
Top, or the top transistor, for the top transistor. Yeah, any of them, they are in sync. All right. So I out equals to actually GM VLO divided by 1 plus GM ZE. Okay. And actually this is GM2. So if I replace this GM2 here, you see that we have a factor of I, okay, and then another factor which is the VLO divided by VT. Okay, so we have two factors, VLO, and then this VLO, and then this VLO is 0.5 volt, and then this VT is just 26 millivolt. So this is 0.5, this is 26 millivolt. Okay. I mean, this is almost 20. 20 times of that one. Okay. Yeah. Just louder, sorry. David, I can't hear you.
GM2 depends on time, in this case. Depends because in the equation you have IRF cosinus WRF times T. In the equation of GM2.
It means a small GM. How this big GM2 comes?
Yes. No, actually,
It should be only IE or,
you mean that I should not put this part, yeah?
and it should be like divided by 2 because there is like a differential input. I mean, because GM should be like, yes,
You mean this one?
yeah.
Yes, you are right. Actually, you are right. You are right. Okay. But anyway, there is no difference in our. So I put it VT. Thank you. So this is 20 actually. Big GM2 is actually the a small GM2 1 over a small GM2 plus Z. This is what we have. Sorry. GM2 is for this one. GM1 is for this one. So this is GM1. This is GM2. Big GM2 is when we assume that here is connected to ground. What is the GM if here there is nothing here? Okay. I mean, we apply all these to the big GM.
you look at the lower transistor to be just integrated.
Sorry?
You look at the lower transistor to be just integrated.
Yes. I mean, I replace all these as ZE.
It's like you connect the base of the lower one connect to ground as well.
The lower one connected to the ground, right?
The RF, the VIF, you connect to the
No. We have a transistor. When we look at the collector of this transistor, then what's the impedance of that? We replace it with Sorry?
Collector is ground for the big GM2.
Yes, the collector, no, the emitter of this, the upper one is connected to ground for big GM. Yes, the emitter of that one. Okay. Anyway, what I want to say here is that when we have something like this, that this is 20 times of that, it means that instead of applying a signal like this, then it amplifies and get saturated by the power supply, and what we see is like this. And then it gets saturated by the power supply. I mean, what we see is a kind of a squared shaped signal. Okay. Sorry?
Where does BT come from?
VT is a thermal voltage. VT equal to 26 millivolt.
Why this GM2 is equal to IE divided by 2? Small GM2.
Because we have two transistors. We have two transistors and the current is divided.
Emitter current is divided.
Yeah. So what we see instead of a sine use is a square-shaped signal. And then we have to write down the equation. I mean, guys, we have to replace the square-shaped signal with its Taylor series and then see that what's the exact value for, I mean, the component that we are interested, which is the LO. If I have it correctly here, then I can write down then if we say that VLO is much higher than VT, then you can write down I out equals to 4 over pi cosine omega LOT minus 4 over 3 pi cosine 3 omega LOT, and then plus so on. And then this multiplied by IRF. And then IRF equals to big GM VRF. Then I out equal to 4 over pi big GM cosine omega LOT VRF. is divided by 2, I think. It's wrong here. This is also divided by 2. Then we can say the I out divided by VRF equals to 2 over pi GM, and then the conversion gain, which is equal to V out or VIF divided by VRF equals to 2 over pi GM RC. And this big GM equals to what we had, that one, GM divided by 1 plus GM Z of E. Okay. Just solve it by yourself. Could be wrong, I don't know. But I think this is correct. All right. So in the last question, so we apply the VRF and VLO, both of them, to the base of this transistor. Okay? And then again we want to find the voltage gain if the LO is a square wave. So we already know that LO is a square wave, and now we want to see that what's the conversion gain or the voltage gain, because we apply the RFE here and then we get the IF here, so it's conversion gain. Okay? So the V of the mixer equals to VRF multiplied by VLO, and this U means square shapes. Okay, which equals to VRF times 4 divided by pi cosine omega LOT minus 4 over 3 pi cosine 3 omega LOT plus the rest. And then these we filter out with this one, and then the only term which is remaining is this one. So this is equal to 4 over pi VRF cosine omega LOT. All right, and then the output current, I mean the I out, equals to IS e to the power VBE plus V in divided by VT, and this VBE is the bias, I mean the DC one, and the V in is the the vmix that we applied. Okay. So this is equal to IC e to the power VRF plus VLO divided by VT. I mean the AC, the AC component, and it's equal to IC e to the power VRF divided by VT e to the power VLO divided by VT. And then if we just replace down e to the power x, so this is e to the power x with 1 plus x plus x squared 2 factorial and so on. And then I assume that the rest is going to filter out by this filter. The only component that we get is this one. So then I can write down this is equal to GM 4 over pi VRF divided by VT cosine omega RF T cosine omega LOT. And then the V out is I out RC, and then the gain or the conversion gain of conversion equal to GM 2 over pi multiplied by RC divided by VT. And then we have the numbers, you can just replace and then find the values. We have the value for the RC, we have the VT, we have the IC, we can find the GM and done. So the main thing that you have to see is this one. I mean, we have a one VT here and another VT here. So in this situation, our conversion gain is, the G of conversion is proportional to 1 over VT squared, not 1 over VT. The dependency on the VT is higher. If we apply a square signal instead of a sine wave signal. All right? I will upload the solutions, or maybe I already uploaded, I don't know. And then you can follow that one as well. So we can have a quick quiz, and then Hope you will have a good break. So please log into Mars. So we have a phase detector as a mixer. And then we want to see that what's the maximum gain of this phase detector. Reference signal V1, the output of the VCO is the V2, and then we have the output of the filter as the main phase detector. Did everybody answer? Okay, I close the all right. So the output, the VM equals to V1 times V2 and equals to AB sine omega t sine omega t plus phi, and then this is equals to AB divided by 2, I think, cosine, for example, phi, I think. Is it correct or not? Is it cosine or sine? This is sine or cosine? Cosine phi plus cosine 2 omega t plus phi. So we filter out this, we have this one. And then, so the maximum output, the maximum gain. So what's the gain of the phase detector? The gain of the phase detector is the dV divided by d phi. And this is equals to AB divided by 2 sine of phi, negative this one. So this is the output, and then for example, phi equals to 90 degree, you can get the maximum value, and then the gain of max is AB divided by 2. So the gain is because the input is phase, and the output, we have to find the output based on the phase. So it's dV divided by d phi. Okay? All right. So question 2. So we have 4 filters, and we want to see that which one is the best one as a loop filter in a PLL design. Done? No? Done. Okay. So if D is wrong, then what should we do? So I'm very happy that everybody answered correct. Yeah. So D is the best one because it gives you more degree of freedom to design your filter. Also, this is a band pass filter. the band pass filter, always we can make it as narrow as what we want, and then it has less phase noise. So this is also another advantage of this. We have two more topics, one on filters and one on the different class of amplifiers on week, hopefully 10 and 11. Few questions are remaining that I have to solve for you. Hopefully on week 12 we can talk, I can revision. We can have a revision if you want. We can also solve few questions, and then yeah. All right. And then so the SETU will be open on week 11. Okay, so we can have a deal then. So the SETU, if more than 80% of the people are participating in SETU, then we can have an extra lecture, extra question solving on week 13, and I'm going to solve the questions for the previous exams on week 13. But it depends on by end of the week 12, we have more than 80% of people are participating in SETU and gives their feedback, their bad and good feedback. Okay? Thank you very much. And submit by time. That's it. Sorry? No. The design project. But you can start, because it is independent, you have to design 6-7 parts. You can start with those.
Okay.
Yes, you have to design a mixer, an LNA, a filter, oscillator, output amplifier, so it has different parts. Matching circuits. So it's not...
I had a question with this one.
Yep.